Hello, Math Analysis. This is your last video for Chapter 4. It is Section 4.6. It is on graph coloring. So yesterday in class we looked at how many colors it would take to color the map of the United States, and we came to the conclusion that it would require 4. Here's a new vocabulary word for you. The chromatic number represents the minimum number of colors it takes to color a graph. This problem has been studied for a very long time, back into the 1800s, and they could never prove it until the late 70s when Kenneth Apple actually used a computer and checked a total of 1,936 smaller cases. So very interesting. So today we're going to actually learn how to color a graph. We're going to start with this problem here where we have 5 students from Hinsdale Central. Each of them are officers in one of the 6 clubs mentioned above, and we're trying to figure out what is the minimum number of days it will take for all of these clubs to meet, because the officer needs to be at the meeting for each of the clubs that he is in. So we're going to start by trying to figure out, well, what would the vertices represent in this graph, and what would the edges represent? So if you were able to look at that and figure out it was 3, very good, but most people can't do that. So the first thing we would talk about is that it's not that the students themselves are with conflict with each other, it's that the clubs that they're in are with conflict with each other. So the vertices will represent the clubs, and then we always use the edges to represent conflict. So once again, we are going to start by writing the clubs as our vertices. And then if we go back and we look, Matt was a member of the Math, Honors, and Science Club. So we will connect those 3 clubs because he cannot be at all of those clubs on the same day. And Marty was a member of the Math, Pep, and Art Club, so we'll connect those. And looking at Kim, Lois, and Dot, there was only one more edge that needed to be drawn in, and that was from Honors to Spanish. So now that you have your graph made, all you need to do at this point is go around and look at the degree or variance at each vertice. So Math has 4, Spanish has 1, Honors has 3, Science has 2, and Art and Pep also have 2. So the way you do this process is that you want to choose the vertex with the highest degree because there's the most conflict with that club. So we're going to make Math one color. After I choose to make Math a color, I'm going to look around and decide, are there any other clubs that are not adjacent or attached to Math with an edge? Because that means they could meet on the same day. And so I decide that Math could also meet on the same day as Spanish. The next step is to look at your remaining vertices that do not have color on them. Find the one with the highest degree and color that your next color. So as we look at this, we see, well, Honors has a degree of 3, Science, Art, and Pep 2. So we're going to make Honors pink and then decide who else can be pink. So either it can be Pep or Art, but notice it cannot be Science. And so here we go, we make those 2, and that leaves me with Science and Art meeting on the same day. So if I had to make a schedule, I could use 3 days for all of these clubs to meet. Notice it's not a unique answer because we could have chosen Art to meet on the same day as Honors. Okay, we're going to move to maps now. The way we color maps is very easy. We start by placing a vertex in each of the regions. And then any regions that share a border need to be connected with an edge because it means they're in conflict because they cannot be the same color. So take a minute and see if you can draw all of the correct edges in. All right, put the machine on pause and restart. Did you get this? Very good. Now we are ready to color this map. So you're going to look for the region that has the most amount of edges in it, which is this guy right here in the middle. So we're going to start by making him one color, and if anybody else is not adjacent to him, he can also be colored the same color. So here we go, and these 2 can be the same color. Then we look for the next vertice with the highest degree. It will either be this guy here or this guy here. So I'm going to make one of those another color, let's say yellow, and the other vertices that are not adjacent can also be yellow. And then my remaining 3 vertices will be pink. Once again, notice the chromatic number for this graph is 3, and the coloring is not unique, but the chromatic number is. We could see that we could have different colors here. Okay, you're going to try it on a very outdated map of South Africa from 1980. 2 things I need to point out about the map is that Namibia and Zimbabwe, the 2 countries in green, just touch at a point, so they could be the same color. But if you look at the countries circled in red, Zambia and Botswana, Even though it looks super tiny on our map, that shared border that I highlighted in yellow is actually pretty large. So Zambia and Botswana cannot be the same color. All right, so please start by putting vertices in each of your countries in Southern Africa and connect them with the edges for showing which countries share a border. So take a minute and try that. Put your machine on pause and see, did you get this? All right, so now we're going to color this map. Look for the country with the highest degree. Obviously, that's Zambia in the middle. And anybody not attached to him could also be that color. But we notice that Zambia is adjacent to each and every one of the other countries. So Zambia is the only country that we could color yellow. We're going to look for our next highest degree, and it's either at Mozambique or Tanzania. So I'm going to choose one of those and any vertex that's not adjacent to that country. I chose Zaire and Botswana. And finally, we're going to look for the next highest degree, Tanzania. And we're going to make Angola and Zimbabwe the same color. And then we will choose our fourth color. So the chromatic number is 4 for the Southern Africa map in 1980. All right, and finally, we're going to look at a problem from your homework tonight. So this problem deals with chemicals that cannot be stored in the same lockers. So the first thing you need to determine is what should the vertices represent and what should the edges represent. So in this problem, what do you think the vertices should represent and the edges? All right, take a look if you were right. The vertices obviously are going to be the chemicals, and the edges will represent which chemicals cannot be stored together because they are in conflict with each other. So I'm going to draw 7 vertices. I'll probably just put them in a circle. And now 1 cannot be stored with 2, 5, or 7. So you're going to draw an edge from 1 to 2, 1 to 5, and 1 to 7. 2 can't be stored with 1, 3, or 5. So you'll draw an edge from 2 to 1, which is already drawn, 2 to 3, and 2 to 5, which is already drawn. Okay, so go ahead and make your graph. Put the machine on pause. All right, how did you do? Nice job. All right, so now it's time to color the map. And we notice that chemical 5 has the most conflict. So we're going to start by coloring that chemical, and either 3 or 4 could be the same color as chemical 5. And then I'm going to look for the next most chemical. It's either 2, 1, or 7. So I decide to make these 3 in their own container, and finally 1 and 3 could be stored. Once again, the answer is not unique in terms of which chemicals belong in which locker, but the chromatic number is. Tonight's homework is 1 to 13. Good luck.